Thanks, Legend, and all the organizers for the workshop. It's really great to be here, and thanks for inviting me. It's also great to hear from Dan. I think we're thinking about similar things, so there might be some overlap in some of what I'm going to be talking about today. So this work is joined with some of my collaborators, two of my colleagues at Purdue, Vinayak Rao and Phyllis Ju, as well as Robin, who we all know here. In particular, I want to thank Phyllis for running all of the simulations and experiments. She spent a lot of time on the coding part of this and put a lot of work into it. So, really big picture, a key benefit of differential privacy is that we know the mechanism, and we want to incorporate that into our statistical inference, both to make sure it's valid and to make sure it's as powerful as possible. And now this is similar to something that Dan presented, where we might have two different frameworks we might think about. One is where we view the data set as sort of the truth or the target of our inference. In that case, that's the left side, where we have some data set X. We apply a mechanism, we're calling that eta, and out comes some Z, that's our privatized output. That's all we have to work with. And in this case, we're trying to infer something about the original data set. And so in this case, the only source of randomness is from the privacy mechanism, and we're trying to understand X. But from statistics, we might be more likely to think in the second scenario, where X is a sample from some model. So there's some population proportion, theta, that we're really interested in. There's some model we propose, F, that shows how the data was generated. And normally that's all we have to deal with. We just have X given theta, we're trying to infer about theta. But now the privacy mechanism adds one more line to our problem, which is the same as on the left side. We don't get X, we get the Z given X from this eta, which is the privacy mechanism. So now all we have is Z. And we're trying to infer about theta, but now there are two sources of randomness. There's randomness from the mechanism and the randomness from the sampling from the model. I'm not trying to say one is more important than the other, these two frameworks, but this talk we're going to focus on the right side. So we have this, the randomized data Z, and we want to infer about theta, and one of the key concepts in statistics is the likelihood function, which says something about which parameters are more likely to have generated the data that we observed. And when you don't have the privacy mechanism, this likelihood is really just based around the F, which is the model. But now we have to incorporate F and eta, both the model and the privacy mechanism. And this appears as what we call the marginal likelihood, where we have to integrate over all the databases that we didn't get to see. And whether you're frequentist or Bayesian, you're still going to be focused around this likelihood function. The posterior distribution is just the prior times the likelihood. So this is really a key concept that we want to understand. Okay, well, we've written down what it is. We have a formula. What's the problem? Well, this integral is over the whole space of possible databases. If we think that maybe each row of our database is an individual, and then each person's contributing a d-dimensional vector, then one database is of size nd, and this is now a huge high-dimensional integral that we probably can't do exactly and would even struggle to do computationally without methods tailored to this problem. So this is what we're broadly focused on in this project, and I want to point out that there have been several works tackling this from many different perspectives. But to kind of summarize the weaknesses of the prior approaches, they tend to be either approximations where they aren't working with the exact likelihood, they introduce some sort of approximation, or they're focused on very specific settings where they have a particular model or a particular mechanism or all of the above. So in contrast, we're proposing a general sampler. So a Gibbs sampler we'll talk about in more detail, but this is a method of sampling from this posterior distribution. And some of the highlights is that we're targeting the exact correct posterior. There's no approximation except for the sampling. And it only requires minimal assumptions. So we're assuming that you can sample from the model without privacy. This is usually not a hard assumption. We have the privacy mechanism. We're assuming we can evaluate the density of that. And finally, that if privacy was not an issue, that you have some sampler for the non-private posterior. This could be an MCMC procedure, doesn't really matter, but there's some way you have of sampling it without privacy. And so besides those three requirements, there are no tuning parameters, there's no other decisions you really have to make or mechanism-specific calculations. We give an easy add-on that allows you to modify your non-private sampler for the private setting. And interestingly, along the way, we proved that we can give a lower bound on the acceptance probability of our sampler, showing that it's provably efficient, it's mixing well. And also, we find that the higher the privacy, the lower the epsilon, we actually get a more efficient sampler. And at the end, we'll talk about an application to a log linear model to show the types of things that we can do with this sampler. So a traditional Gibbs sampler, so we have our observed data, which is the noisy Z, and all the parameters of our model, well, we have the theta we care about, and then we have all the x's we didn't get to observe. And the way a Gibbs sampler works is it iterates through all the different parameters and samples condition on the other parameters. So the first step, you would sample theta given all the x's and the z. This is equivalent to just theta given x, and this is just the non-private posterior. We're assuming that you can do this. Also, an MCMC procedure is fine here. And then in step 3, we're sampling one of the x's given the other x's and the theta and the z. And this is what's really the troublesome step that we're going to focus on. So if to visualize what's happening with the Gibbs sampler, we're taking these steps that are orthogonal to each other in this illustration here. And over time, as we run this, we approach the correct distribution that we're targeting. So a simplifying assumption, this isn't strictly necessary, but it makes it a little easier to reason about, easier to look at for the talk. We'll assume the x's are independent. So this simplifies line 3, where now x is just given theta and z. So now there's really just two steps. There's sampling theta given x. This is the problem we're assuming you can solve without privacy. And then the challenging step is x given theta and z. And that's what we may not know how to do. So the reason it's difficult is that x given theta and z depends on both your model and the mechanism. For certain problems, you might be able to work this out exactly, but you would certainly have to do calculations for that specific case. And we're going to assume that you're maybe not willing to do that or unable to do that. But we could approximate this by a much simpler task of just sampling x given theta. This is just sampling from the model. And if you have a generative model, this should be straightforward. But because this isn't technically the correct step in the Gibbs sampler, we're going to need to add an accept-reject step to our Markov chain. So that's what happens in line 4. And interestingly, when you work out what this acceptance probability, you end up just looking at the ratio of the eta, which is the privacy mechanism, and all we've changed is one data point. And this should start to ring a bell that this looks a lot like the privacy definition. And so actually we can use some properties of this privacy mechanism to say something about this acceptance rate. So of course with pure differential privacy, we look at the ratio of eta, where you change one person. This is bounded by e to the epsilon on the top, and for our case, we're interested on the lower bound of e to the minus epsilon. So if our eta satisfies differential privacy, we know this acceptance probability is at least e to the minus epsilon. And even more interestingly, the more privacy we have, in which case the noise is causing more issues with inference and we care even more about correctly adjusting for it, this acceptance rate improves and our sampler gets even more efficient. Even for a moderate epsilon of 1, we already have a 36% acceptance rate, which is generally quite good for a Markov chain. I did steal this figure from the UK government. You might be worried about some other things with the sampler besides just the acceptance rate. One thing is evaluating the eta. You might be worried that this is an expensive operation because we have to plug in n data points. Does it take order n time? Well, many mechanisms only depend on some sum over the data points. For example, many exponential mechanisms deal with some empirical risk. If you're adding noise to sufficient statistics, those are usually sums as well. So you can update from 1x to an x prime, but different one interest by just subtracting and adding 1 point. So this is actually only constant time to adjust from one data set to another. And when you look at the whole one run through our sampler, this takes order n time, which is the same as many non-private samplers as well. So not only can you take a working non-private sampler and modify it to target the correct thing, but we can also say that it takes about the same amount of time to run as your non-private sampler. So we're going to look at an application now to see what types of problems we could tackle with this. I view this still as sort of a simple application, but that's not entirely non-trivial. So it is still kind of a simple example. So this is what's called a naive Bayes classifier, which is a type of log linear model. We have, it's all on discrete data. So we have features and we have classes. And we're assuming the data are IID. And the purpose of this model is usually to try to predict the class given the feature. And the key assumption of the model is that the features given the class are independent, which is a strong assumption. But it tends that this classifier, while it's simple, it tends to work well. And again, this is just one example to illustrate our approach. So without privacy, you can summarize the data in these sort of histograms where you count x cross y, each of the features, how many classes there are. And we're going to add noise from, we're just going to do a Laplace. You could use other mechanisms, of course, but just for this example, we're just adding a bunch of noise to these counts. And now we're tasked with inferring about the parameters of this model given the noisy counts. And this problem setup we stole from another paper that was doing variational inference as a different way of approximating the posterior. So we kind of use that as motivation to look at this example. So for the simulation, we're looking at a small sample size of just 100. We picked 5 for the number of classes and features, and we chose 3 options for each feature. We tried different epsilon values, so this will be interesting to compare both the acceptance rate of our method as well as the posterior inference, how that changes with different epsilon values. And we chose a default prior of a Dirichlet with all parameters of 2. So first, let's look at the posterior mean. So for this simulation, we sample one non-private data set. We're just going to hold that fixed for the simulation. And for that data set, we're going to run and create 100 privatized data sets at each epsilon value. Then we'll run our chain on each privatized data set, run it for 10,000 iterations, and then calculate the posterior mean. And the colored horizontal lines are the posterior means without privacy. And so we see that as epsilon grows, our private posterior mean centers around the non-private. That makes sense, that's good. And then as epsilon decreases, we center around 0.2. And it turns out that's actually the center of the prior distribution. So that also makes sense. And we see that as epsilon grows, we get more informed by the data set and we approach the non-private. And as epsilon decreases, we lose information from the data set. We basically get the prior back. Yes.
Sorry, what are the 5 panels?
Yeah. So actually, I should have explained on that slide. So I explained on this slide, it's the just the marginal probability of the classes. We just kind of chose a few parameters to look at just to illustrate. So it's probably that y is equal to I. So probably that y is 1 versus 2, 3, 4, or 5. Yeah. So there are many more parameters in the model, but just for illustration, we just looked at these 5. So another thing, so this is because I tend to think in a frequentist kind of setting. Well, we're doing Bayesian, but I can still pretend it's a frequentist estimator. So we can make 90% credible intervals and now ask what's the coverage of these intervals for, again, the same 5 parameters. So in this case, we run the prior once. So we get one set of like true parameters, which are in the top row. And then now we're doing the same procedure where we're running, getting data sets and applying randomness, running our chain, computing credible intervals, and calculating the empirical coverage. Now, because the sample size is only 100, we don't really expect perfect coverage here because the asymptotics probably haven't quite kicked in. But we can still look and see if they're in the ballpark. And we see most of these entries are around 0.9 or higher. There are 3 key exceptions in the top right where they're significantly lower. And my interpretation of these is that this is with very low epsilon, and P4 is the highest value, which is far away from the prior mean of 0.2. So with a small epsilon, our posterior is being forced close to the prior, and we're probably missing this value because it's kind of out of the ordinary from our prior belief. But setting that aside, if you look over the whole table, the average coverage is over 0.9. And even at the epsilon of 0.1, the average coverage is 0.87. So overall, we're getting the right sort of behavior we would expect. And then last, we'll look at the acceptance rate. So if you recall, we had this lower bound on the acceptance rate, e to the minus epsilon. That's shown in the black line here. But because that's a lower bound, it could be that on average, it's actually quite better, and we don't know. So here we've run our chain several times, and in blue is the average acceptance rate, which is significantly higher, as well as the observed minimum acceptance rate in yellow, which is even still somewhere higher than the lower bound. So overall, we've got a general sampler to do posterior inference on the privacy problem. It has the correct target distribution. And I think one of the key things is that it's very user-friendly. If you can do posterior inference without privacy, here's a simple add-on. It's mechanism independent. You don't have to do any calculations on the mechanism or your model. There's no tuning parameters, no real decisions you have to make. It's just a simple plug-in, and it works. And also, the more privacy you have, the more efficient the sampler gets, which is sort of just an interesting phenomenon by itself. So this is a work in progress. We're planning to get it online hopefully next month. Feel free to, happy to take questions, or if you want to email me afterwards, happy to talk. Thanks.
Maybe I can ask a quick clarification question.
Mm-hmm.
Could you please go to page 10?
Sure.
Yeah, I was just curious, say how the independence of xi's can simplify the third step.
Yeah, so
because given ZDP, xi and x minus may not be independent, right?
Let's see.
So in a way, I guess the answer actually is on the next slide, because we are not sampling from that. We are sampling from the model that is actually just a generated model. And usually, not always, but a lot of times we do assume conditional independence of the data given a parameter. So it's just the it reduces the dimensionality of the computation.
But given ZDP, the data are not independent.
They may not be, no.
That's right. The rejection rule accounts for that, yeah. So
Okay.
I think maybe, yeah, to be more clear, perhaps we should have said the approximation first and then applied the independence to be a little more precise.
So then how does the independence help here, if you can directly use this rule?
Yeah, so really, the key idea is just dropping z from the right-hand side. So if you didn't have independence, then here in our approximation, you would just do xi given the other x's and theta. So that's really our idea. The independence just lets us write this simpler, so you don't worry about the other x's. But you don't really need to make that assumption if you can do xi given the other x's.
Okay.
Yeah.
Right. Thank you.
And then the accept reject would still be the same. It just comes down to the mechanism.
Okay.
Yeah. Thank
Thanks.
you.
Any other questions? Oh,
I think this is very interesting work. Thank you. I really like this observation, especially about the DP bound coming in the acceptance probability. It's very nice. One thing that I was just thinking about is you're always using the prior distribution sort of as the proposal here.
Well, it's the model, not the prior.
Oh, sorry. You're using the model distribution as the prior, which depending on, depending on whether you have strong observation likelihood, feels like it may or may not be like good for effectively exploring the space. Is there ever a situation where you would want to use a different distribution there? For example, that like if you like suppose epsilon was very large, would it be possible to take into account the likelihood for the proposal?
Yeah, so you definitely could use other proposals. And yeah, I think what can become an issue is, let's see if I can think clearly. Let's say epsilon is really high, where it's ridiculously high. Then it might be that maybe there's only like one x value that can kind of solve the equation of producing the z.
Yeah.
In which case, this acceptance probably could go really low, and you might then maybe you do want to choose a sampler that's kind of looking locally rather than over the whole space. So there's definitely room for some adjustments with that. Yeah. We're also working on some more sophisticated methods to try to get around some of these other issues, but I just want to focus on like the simplest method for today. Yeah.
Okay, thank you very much.